Now let's consider pH effect. Uh, Many times its solute is acid or base, so its charge changes as the pH is changed. Usually, neutral species are more soluble in organic solvent than in aqueous solvent. Okay. In the meantime, charged species are more soluble in aqueous solvent. Okay. This is a general fact. Now consider a basic amine. Okay, amine B. Okay, and the page one is aqueous solution, and page two is organic solvent. Okay, and here you see we define the distribution coefficient D. Okay, equals total concentration in phase 2 divided by total concentration in phase 1. Okay, since this base can accept can take the proton. Okay, so it exists in a aqueous solution as P or pH plus. Okay, but in organic solvent, in a neutral species only exists. Okay, so in organic in phase two is organic solvent, and only this form B exists. Okay, in phase two. All right, and we substitute this partition coefficient K equals uh, the uh, the concentration of B in phase two, and divided by the concentration in phase 1. Okay, and here this one Ka is what? Hmm? The dissociation constant of pH plus. Okay, it is given by this equation. And this is a simple equilibrium constant. Okay, and then now we substitute this K and Ka into the equation for D, and then we rewrite this distribution coefficient. Okay, D equals K multiplied by Ka and divided by Ka plus proton concentration. Okay, oh, now you see, you are very familiar with this one. Ka divided by Ka plus H plus. This is the what? The fraction of the form of B. Okay, this is we call alpha B here. All right. Yeah. D is expressed by this very simple equation. Okay, where alpha B equals this one. B no, concentration B in aqueous solution divided by the B aqueous plus pH plus aqueous. Okay, and let's look at this figure. This figure shows the change of D, yeah, expressed in log D, okay, as a function of pH. All right, you change the pH, and then you can change this proton concentration. Okay, and D changes at a very acidic condition. In the case, the proton concentration is very high. This one is very high, and what the D becomes lower. Okay, it becomes smaller and smaller. Since this one becomes higher, and then as pH increases, this one becomes smaller and smaller, and then the D also increases. Okay, with pH change. Okay, but after some certain pH, the D doesn't change much. Okay, why? Yeah? In that case, I think uh, this one alpha B reaches almost 1. Okay, so at higher pH, okay, the alpha B value doesn't change. Okay, it already reaches 1. Okay, that's why it's log D is leveled off here. Okay? Yeah. So look at this one. The but what if let's see, and let me see, here it changes as a slope when you see pH equals pKa here, okay? pH equals pKa, and then what? pH equals pKa, and at this point this slope changes, okay? And below pKa, yeah, then the main species is pH plus, but after pKa is the main species B. Okay? This is the simple acid-base chemistry, okay? And well, this equation is for base, okay, base, but we can derive with the same equation for acid, okay. This is a challenge for you, okay. Distribution of acid between two phases, D equals this one, given by this equation. In this case also, D equals K multiplied by alpha HA, okay. Alpha HA is the fraction of HA form in aqueous solution. Okay? Uh, this is left for you. All right. Yeah, here is an example: effect of pH on extraction. Okay, let's read this question. Suppose that the partition coefficient for an amine B is K equals 3.0, okay, and the acid dissociation constant of pH plus is 1.0 times 10 to minus 9. If 50 ml of 0.01 molar aqueous amine are extracted with 100 milliliters of solvent, what will be the formal concentration remaining in the aqueous phase at pH 10 and at pH 8? Yeah? Okay, and it is very easy actually. So this one actually asking us to calculate, let's see, uh, the the distribution, this one distribution coefficient, okay. And at the pH 10 we use let's see, this one, so since we are uh, dealing with this amine base, okay. Here we use this equation, and here the proton concentration, yeah, is 10 to minus 10 at pH 10, okay, and we input the necessary constant, and then we get 2.73. That's the distribution coefficient, okay. And using D, we can calculate the Q, okay. Here is the let me see, let's see, Q in place of K, using D. In this case, this Q is expressed here. Look at that, Q here, okay. But in this case, yeah, let's use D instead of you know K, instead of yeah, we can use what, the D in place of K, okay. And the small q is 0.15, okay, which means that 50% of amine is left in water, okay. So concentration of amine in aqueous phase is what? Aqueous phase is this one, 0.15 multiplied by original concentration, which is 0.01 molar, right? So this amount, this concentration, yeah, of 1.5 millimolar still remains in aqueous solution, okay. The same calculation is done at pH 8, okay. First you calculate the D here, all right, which is 0.273, okay, and then Q is 0.65, so 65% left in water, okay. So in terms of molar concentration, 6.5 molar, right? So here, we conclude that at the low pH, more uh, you see more base, yeah, more base, which is amine here, more amine remains in aqueous solution. Okay, yeah, as pH uh, y, because the distribution coefficient here it becomes smaller as pH goes low. Okay, the small d means more concentration, more amount in aqueous phase. Okay, yeah, we can this example demonstrates, okay, that fact. And we can use the metal chelator, yeah, for the solvent extraction. The neutral metal complexes soluble in organic solvent, okay, because it doesn't have any charge on it, so soluble in organic solvent, so extractable with organic solvent. Selective complexation of one metal ion in ionic mixtures. Okay? Yeah, these complexing agents are used to extract metal ions, right, into the organic solvent. Yeah, this one hydroxyquinone, quinoline, and uh, uh, cuperon, right? This one and this one, titazone. Okay, and this is good for lead ion, and this is very when after the complexation with the metal ion, and it forms like this one. Okay, yeah. And ligand can be weak acid HL. Okay, ligand itself, in many cases are acid, but weak, yeah, weak acid. Okay, and for example, this one, it produces protons after complexation here. Okay, yeah, and because this let me see, it's after complexation with. Oh, by the way, this is the. Let me see. Uh, Let me see how the lead ions are made complex with this one. Two of these species now make a complex with lead ion. Okay, and as a result, this one, two protons are produced. Okay, and here, this is sulfur. Hmm? Sulfur, you know, coordinated protons are released. Okay? So since ligand also in many cases are weak acids, then we can write this ligand dissociation. Okay, it dissociates one proton, and then we write the equilibrium constant, dissociation constant for this ligand. Okay, is given by this one. Okay, it applies only in aqueous solution. All right, and you know, and ligand no, may have complex with one metal ion. Okay, this one MLN. Okay? So for this reaction, we write the beta. Okay, beta. This is also equilibrium constant. Okay, in this case, for this reaction, it's N ligand. Okay, so if we consider stepwise complexation, first one ligand and one metal ion, and then Ml1 and then Ml1 plus another metal ligand, and then in the case we write the equilibrium constant K. Okay, but this is cumulative what equilibrium constant. It is given by this equation. Okay. let's drive an equation for distribution coefficient of a metal between two phases. Okay, here the low part is in this case now organic phase, such as this one CHCl3. Okay, this is since it contains chlorine, three chlorine atoms, so this is heavier. This density of this one is much higher than water. Okay, in this case, the aqueous phase is above this organic phase. All right, and okay, this one only neutral species exist in organic phase here, and not only neutral species but also charged species exist in aqueous phase here. Okay, and this one, this distribution HL, this is neutral species distributes between aqueous and organic phases, and then here we the equilibrium constant here. This is partition coefficient. Yeah, KL equals this one. Yeah? HL organic divided by HL concentration in aqueous phase. Okay, and another one equilibration is this one MLN. This one. Okay. This is also distributed between two phases. Okay, it's because they are, they are all, the neutral spaces. Okay, then we define that Km. The definition is the identical by with this one. Okay, KL, and the distribution coefficient equals total metal concentration in organic phase divided by total metal concentration in aqueous phase. Okay? It is maybe approximated by this one, this equation. Uh, the total metal concentration in organic phase is only this one, MLN, right? But in aqueous phase, there are two species that contain metal species. Okay, here M, this one, and this one, MLN. But as this the arrows indicates, right, this metal ligand complex mostly exists in organic phase. So the amount of metal MLN in aqueous phase is very little. Okay, so we simply ignore this one, and then T can be approximated by this equation. All right. Yeah. And MLN organic phase equals what? Here Km multiplied by this one MLN aqueous phase. Okay, and this one is given by this equation Km, and here we already wrote this one, and Km beta and M, metal ion concentration in aqueous phase, and ligand concentration and power, yeah, in aqueous phase, right? This one. Oh, now equations become more and more complex, so you carefully follow me. Yeah, so this organic phase, in organic phase, this MLN concentration is given by this one. Okay, uh, so from here, organic phase MLN, right? Uh, Instead of using this one, ligand concentration, uh, we can use other, let me see here, ligand concentration. We can use the beta. Okay, and this equation we get, right? This one is already very complex, yeah, very complicated. Okay, and D, let's see, D is given by this one, and then it can be written, it can be approximated by this one. Okay, here let me see, D is actually defined by this one, and yeah, this one may be removed, okay, because here, and it becomes this part, yeah, right? And the HL concentration in aqueous phase is given by this equation, okay? This is a simple let me see, arrangement of this one, okay? Yeah, here. So distribution of metal chelate complex between phases, which is D, okay? D equals Km multiplied by beta and multiplied by Ka nth power divided by KL nth power, okay? Or let me see, KL here, yeah? Instead of this one, we use this one, okay? And multiply by HL concentration nth power in organic phase and divide by proton concentration nth power, okay, in aqueous phase. Wow, this is already very complex, very complex. This figure shows the extraction of metal ions by dithiazone, okay, into this one is let me see, CCl4, carbon tetrachloride, okay. This is also very heavy solvent at pH 5. You know, copper ion completely extracted into CCl4, whereas lead ion and zinc ion remain in aqueous phase. Oh, how do we read this figure? Okay? This one, x-axis is pH here, pH, and y-axis is percent extracted. Okay, let's see. At pH 5 here, uh, carbon kappa, divalent kappa is here. Where is it? This divalent kappa. Okay, at pH 5, this percentage extracted already 100%. Okay, so completely kappa is extracted into CCl4, but lead here and zinc, yeah, these ions, and also thallium and cadmium ions are not were extracted into the what into the organic solvent like carbon tetrachloride, okay, at pH 5. So to extract these ions, so pH should be increased, okay, yeah. So this figure tells that information, all right. Okay, let's start here, stop here.